Okay, so welcome back to another video. Here's a hyperbolic, our hyperbolic function integral that we want to calculate. So we have the positive reals we're integrating from 0 to positive infinity of the hyperbolic tangent of x divided by e to the x dx. So in order to do something like this, I think the first thing we can do is we can actually rewrite our hyperbolic function for tangent x in a form such that it's an exponential function, since we have something of e to the power x in that form. So we can actually write things, or rather convert things a little bit easier, so that we have something of just e basis and then just do a little bit of rewriting. So from there, afterwards, we're actually going to apply a little bit of, well, there will be some calculus techniques involved, of course, but also a little bit of applying some partial fraction decomposition to make the simplification easier from there. So we actually will do a little bit of that exercise just to tackle forward from that. So with that, why don't we actually just jump right in? So it's worth noting that the hyperbolic tangent of x has a nice form of the e basis, such that it's written as e to the power x, the exponential form of the exponential form in this case. So e to the power x minus e to the negative x, then divided by e to the x. Add this with e to the negative x. So I'll substitute this back. So we have 0 to infinity, and then this is going to replace our hyperbolic tangent for this form. So then e to the power x minus e to the negative x to the power negative x, then e to the x, and then multiply by e to the x, add this with e to the negative x, and then dx. Okay, so simplify things a little further. For our numerator, I'm actually going to factor out an e to the power 2x. You will see why we do this. So e to the 2x, and then now factoring that out, so that means that will be e to the negative x, and then minus e to the negative 3x. All right, and so everything we hear, e to the x, and then e to the, positive x plus e to the negative x, and then dx. All right, so now let's actually, of course, now cancel some things out. So then now we're just left with 0 to infinity. So that's just going to get rid of the e to the x on the denominator. So then e to the x multiply with e to the negative x, subtract e to the negative 3x. Okay, and then but divided by e to the x, add this with e to the negative x, and then dx. Okay, so there we have it. So this is what we're dealing with so far. Everything is in terms of the exponential function. So now let's actually perform a nice little u sub. So we're going to let u just be e to the power x. And so of course, differentiating that, so e to the x, and then du is going to be simply just e to the x, and then dx. Okay. So now we just have to do our substitution after just everything, get everything in terms for u. So then now do that. And so if I plug in infinity for x, that's going to be positive infinity. Plug in 0, that's going to be 1. Okay, now to substitute, so e to the x dx, that's just going to get rid of itself. So that'll just be simply just du. And then we just plug the u and everything in terms of here. So that means I have 1 divided by u, the e to the negative x, that's the same thing as with substituting that with a negative 1. So now then 1 divided by u, then minus 1 divided by u cubed. Our denominator is going to be u, and then add this with 1 divided by u, and then du. So let's actually just get rid of some of those denominators above. So and from the denominator of our function as well. So 1 to infinity. So then I'm actually just going to multiply a u cubed into everything, just so all the denominators just aren't appearing. So we have u squared minus 1, then divided by u to the power 4 plus u squared, then du. So I'll just factor out the u squared from our denominator. So then that'll just be u squared minus 1, then divided by u squared multiplied by u squared plus 1, and then du. Okay, so that's all we have left is to calculate this integral. In order to do so, let's actually apply a nice little partial fraction decomposition. So in order to do that, so of course, the forms are different depending on whatever the rational function is. So I'm not really going to go into the sweats of details and all that. You just need to know that for our form of the rational function we're dealing with, so we have, I'm actually in my notes, I had this in terms of x, so I'm actually just going to write this in x for the time being, and then we'll just go back to u afterwards. So x squared minus 1, and then divided by x squared, then times x squared plus 1. Then it has a nice form with our nice little constants, such that this is a divided by x, add this with b divided by x squared, and then add this with cx plus d, and then divided by x squared plus 1. Okay, so all we have to do now is just apply partial fraction decomposition. To do so, let's get everything in terms of the common denominator over here. So we have to multiply some certain terms from our numerator on the right side. So then I'll just use this with a, so x times x squared plus 1. Then add this with b times x squared plus 1. Add this with, so cx plus d, then multiply with x squared, and then set that equal to the other side, left-hand side, x squared minus 1. Okay, so just perform the multiplication. So that means a times x cubed plus x. Add this with b times x squared plus 1 plus cx cubed, and then plus dx squared equals x squared minus 1. And then the next thing to do here is all we have to do is just equate our coefficients from the left-hand side to the right-hand side. So everything in terms for the cube, x cubed, so that means I have a, and over here plus c. There's none x cubed on the coefficient on the right-hand side, so that's just set to equal to 0. So let's see, bx squared and dx squared. So let's see, b plus d. And so we have 1x squared on that side, so that means we set that equal to positive 1. Anything in terms of x, so ax, so that means a is then equal to, and then there's none of the x coefficients, so we set that equal to 0. And then last thing is, we still have the constant itself, so that means b is equal to the -1, so b is equal to -1. So we got that, so we just plug in the formulas that were the constants that we solved for into the new variables to solve for c and d, and see that we get that c is equal to 0, and then d is just equal to positive 2. Okay, so that would have to mean that going over here, so continuing forward with the after applying partial fraction decomposition, our new integral is going to be from 1 to infinity of 2 divided by u squared plus 1, then minus 1 divided by u squared, and then du. Okay, and afterwards, calculating this is just easy peasy, so I can just put the constants out. 1 to infinity of just 1 divided by u squared plus 1 du, and then minus 1 over u, so 1 over u, and then 1 divided by u squared, then du. Okay, then finding the antiderivative or integral is easy, so this is just going to be 2 times arc tan of u from 1 to infinity, and then this is going to be a minus 1 divided by u, but that becomes a positive, so then plus 1 divided by u from 1 to infinity. And then if you actually just plug in everything back together, so this is going to be 2, plug in infinity, this is going to be pi squared divided by 2, plug in 1, so pi divided by 4. Then over here, so that means that's going to be plus 0, and then subtract 1, combine everything together, so that means all this is simply just going to yield out to just pi square, then subtract 1, which is our final answer to our hyperbolic tangent and a combination hybrid of our exponential function integral, just like that. Everything just having to convert things in terms of the exponential function so that we don't have to deal with the hyperbolic function as a whole, then just reducing it down and then applying partial fraction decomposition to make things a little bit simple to calculate the integrals. So yeah, that's pretty cool if you ask me.